In mathematics, the notion of permutation relates to the act of permuting, or rearranging, members of a set into a particular sequence or order. For example, there are 6 permutations of the set 1, 2, 3, namely and. As another example, an anagram of a word, all of whose letters are different, is a permutation of its letters. The study of permutations of finite sets is a topic in the field of combinatorics. The number of permutations of n distinct objects is now factorial, usually written as n, which means the product of all positive integers less than or equal to n. Permutations occur, in more or less prominent ways, in almost every area of mathematics. They often arise when different orderings on certain finite sets are considered, possibly only because one wants to ignore such orderings and needs to know how many configurations are thus identified. For similar reasons, permutations arise in the study of sorting algorithms in computer science. In algebra and particularly in group theory, a permutation of a set S is defined as a bijection from S to itself. This is related to the rearrangement of S in which each element S takes the place of the corresponding F, S. The collection of such permutations form a symmetric group. The key to its structure is the fact that the composition of 2 permutations defines a third rearrangement. Permutations may act on structured objects by rearranging their components, or by certain replacements of symbols. In elementary combinatorics, the K-permutations, or partial permutations, are the ordered arrangements of K distinct elements selected from a set. When K is equal to the size of the set, these are the permutations of the set. History: the rule to determine the number of permutations of n objects was known in Indian culture at least as early as around 1150. The Lilavati by the Indian mathematician Bhaskara II contains a passage that translates to: the product of multiplication of the arithmetical series beginning and increasing by unity and continued to the number of places, will be the variations of number with specific figures. A first case in which seemingly unrelated mathematical questions were studied with the help of permutations occurred around 1770, when Joseph Louis Lagrange, in the study of polynomial equations, observed that properties of the permutations of the roots of an equation are related to the possibilities to solve it. This line of work ultimately resulted, through the work of a permulvarist Galois, in Galois theory, which gives a complete description of what is possible and impossible with respect to solving polynomial equations by radicals. In modern mathematics there are many similar situations in which understanding a problem requires studying certain permutations related to it. Definition and usage: there are 2 common ways of regarding permutations. They are completely equivalent and either form is readily converted to the other. Which form is preferable depends on the type of questions being asked about the permutations. Some disciplines use one form more predominantly than the other. The first way to regard permutations of a set S is to define them as the bijections from S to itself. Thus, the permutations are being thought of as functions and so, can be composed with each other, forming groups of permutations. From this viewpoint, the elements of S have no special properties and are just being used as convenient names for the objects being moved around according to the bijection. In Cauchy's 2-line notation, one lists the elements of S in the first row, and for each one its image under the permutation below it in the second row. For instance, a particular permutation of the set 1, 2, 3, 4, 5 can be written as. This means that I florin satisfies I florin, 1, equals 2, I florin, 2, equals 5, I florin, 3, equals 4, I florin, 4, equals 3, and I florin, 5, equals 1. There is no special order that the elements of S appearing in the first row have to appear in. This permutation could also be written as. However, if there is a natural order that the elements of S can be placed in, say, then under the assumption that the first row of the permutation is in this natural order, the first row need not be written. Thus, under this assumption, the permutation can also be written in one-line notation as, which is the second common way of representing permutations. That is, a permutation of the set S is an ordered arrangement of the elements of S. the permutation above would then be given by, since the natural order would be assumed. This form of representation is common in elementary combinatorics, computer science, and those areas of combinatorics that are closely related to it. In many applications where the elements of S will be compared to each other, this is the preferred form of permutation representation. There are n permutations of a finite set S having n elements. Circular permutations, when considered as arrangements, are sometimes referred to as linearly ordered arrangements. In these arrangements there is a first element, a second element, and so on. If, however, the objects are arranged in a circular manner, this distinguished ordering no longer exists, that is, there is no first element in the arrangement. Any element can be considered as the start of the arrangement. The arrangements of objects in a circular manner are called circular permutations. Two circular permutations are equivalent if one can be rotated into the other. The following two circular permutations on four letters are considered to be the same. 1 4, 4 3 2 1, 2 3. The circular arrangements are to be read counterclockwise, so the following two are not equivalent since no rotation can bring one to the other. 1 1, 4 3 3 4, 2 2. The number of circular permutations of a set S with n elements is k permutations of n. There is also a weaker meaning of the term permutation that is sometimes used in elementary combinatorics texts, designating those ordered arrangements in which no element occurs more than once, but without the requirement of using all the elements from a given set. These are not permutations except in special cases, but are natural generalizations of the ordered arrangement concept. Indeed, this use often involves considering arrangements of a fixed length or k of elements taken from a given set of size n. These objects are also known as partial permutations or as sequences without repetition, terms that avoid confusion with the other, more common, meaning of permutation. The number of such k permutations of n is denoted variously by such symbols as npk, npk, pn, k, or p, n, k, and its value is given by the product, which is 0 1 k, n, and otherwise is equal to. The product is well defined without the assumption that n is a non-negative integer and is of importance outside combinatorics as well. It is known as the Pochhammer symbol or as the kth falling factorial power nk of n. Permutations of multisets. If M is a finite multiset, then a multiset permutation is an ordered arrangement of elements of M in which each element appears exactly as often as is its multiplicity in M. An anagram of a word having some repeated letters is an example of a multiset permutation. If the multiplicities of the elements of M are, and their sum is n, then the number of multiset permutations of M is given by the multinomial coefficient. For example, the number of distinct anagrams of the word Mississippi is. A k permutation of a multiset M is a sequence of length k of elements of M in which each element appears at most its multiplicity in M times. Infinite repetition numbers are allowed in some applications. Permutations in group theory. The set of all permutations of any given set S forms a group, with the composition of maps as the product operation and the identity function as the neutral element of the group. This is the symmetric group of S, denoted by sim, S. Up to isomorphism, this symmetric group only depends on the cardinality of the set, so the nature of elements of S is irrelevant for the structure of the group. Symmetric groups have been studied mostly in the case of finite sets, so, confined to this case, one can assume without loss of generality that SAR equals a 1, 2, n for some natural number n. This is then the symmetric group of degree n, usually written as Sn. Any subgroup of a symmetric group is called a permutation group. By Cayley's theorem, any group is isomorphic to some permutation group, and every finite group to a subgroup of some finite symmetric group. Cycle notation. Another notation for permutations called cycle notation focuses on the effect of successively applying the permutation. It expresses the permutation as a product of cycles corresponding to the orbits of the permutation. Since distinct orbits are disjoint, this is referred to as the decomposition into disjoint cycles of the permutation. Due to the likely possibility of confusion, cycle notation is not used in conjunction with one-line notation for permutations. It works as follows: starting from some element x of S, one writes the sequence I florin, x of successive images under I florin, until the image would be x, at which point one instead closes the parentheses. The set of values written down forms the orbit of x, and the parenthesized expression gives the corresponding cycle of I florin. One then continues choosing an element y of S that is not in the orbit already written down, and writes down the corresponding cycle, and so on until all elements of S belong to some cycle written down. Since for every new cycle the starting point can be chosen in different ways, there are in general many different cycle notations for the same permutation. For the example above, one has, for instance, each cycle of I florin denotes a permutation in its own right, namely the one that takes the same values as I florin on this orbit, while mapping all other elements of S to themselves. The size k of the orbit is called the length of the cycle, and a cycle of length k is called a k-cycle. Any one cycle is the identity permutation, and so, they are all the same permutation. Distinct orbits of I florin are by definition disjoint, so the corresponding cycles commute, and I florin is the product of its cycles. Therefore the concatenation of cycles in the cycle notation is interpreted as denoting composition of permutations, and writing a permutation as a product of its cycles is called a decomposition into cycles of the permutation. This decomposition is essentially unique. Apart from the reordering the cycles in the product, there are no other ways to write I florin as a product of cycles. The cycle notation is less unique, since each individual cycle can be written in different ways, as in the example above where denotes the same cycle as or denotes a different cycle. In writing a permutation as a product of its cycles, it is typical, but not required, to suppress the writing of one cycles when no confusion can arise. An orbit of size E01 is called a fixed point of the permutation. A permutation that has no fixed point is called a derangement. Cycles of length 2 are called transpositions. Such permutations merely exchange the place of two elements. Since the orbits of a permutation partition the set S, for a finite set of size n, the lengths of the cycles of a permutation I florin form a partition of n called the cycle type of I florin. There is a 1 in the cycle type for every fixed point of I florin, a 2 for every transposition, and so on. The cycle type of I squared equals 3 4, 6 8, 7. Which is sometimes written in a more compact form as. Permutation groups have more structure than abstract groups. Different realizations of a group as a permutation group need not be equivalent for this additional structure. For instance, S3 is naturally a permutation group, in which any transposition has cycle type, but the proof of Cayley's theorem realizes S3 is a subgroup of S6, in which permutation group transpositions have cycle type. So in spite of Cayley's theorem, the study of permutation groups differs from the study of abstract groups. Product and inverse. The product of two permutations is defined as their composition as functions, in other words I florin I euro is the function that maps any element x of the set to I florin, I euro, x. Note that the rightmost permutation is applied to the argument first, because of the way function application is written. Some authors prefer the leftmost factor acting first, but to that end permutations must be written to the right of their argument, for instance as an exponent, where I florin acting on x is written xi florin. Then the product is defined by xi florin I euro equals I euro. However, this gives a different rule for multiplying permutations. This article uses the definition where the rightmost permutation is applied first. Since the composition of two bijections always gives another bijection, the product of two permutations is again a permutation. In two-line notation, the product of two permutations is obtained by rearranging the columns of the second permutation so that its first row is identical with the second row of the first permutation. The product can then be written as the first row of the first permutation over the second row of the modified second permutation. For example, given the permutations, the product QP is. In cyclic notation this same product would be given by Since function composition is associative, so is the product operation on permutations, AI equals I florin A, I euro AI. Therefore, products of more than two permutations are usually written without adding parentheses to express grouping. They are also usually written without a dot or other sign to indicate multiplication. The identity permutation, which maps every element of the set to itself, is the neutral element for this product. In two-line notation, the identity is. Since bijections have inverses, so do permutations, and the inverse I florin A1 of I florin is again a permutation. Explicitly, whenever I florin, x, equals y1 also has I florin A1, y, equals x. In two-line notation the inverse can be obtained by interchanging the two lines. For instance, in cycle notation one can reverse the order of the elements in each cycle to obtain a cycle notation for its inverse. Thus, having an associative product, a neutral element, and inverses for all its elements, makes the set of all permutations of S into a group, called the symmetric group of S. Properties: every permutation of a finite set can be expressed as the product of transpositions. Moreover, although many such expressions for a given permutation may exist, there can never be among them both expressions with an even number and expressions with an odd number of transpositions. All permutations are then classified as even or odd, according to the parity of the transpositions in any such expression. Multiplying permutations written in cycle notation follows no easily described pattern, and the cycles of the product can be entirely different from those of the permutations being composed. However, the cycle structure is preserved in the special case of conjugating a permutation I florin by another permutation I euro, which means forming the product I euro AI florin AI euro A1. Here the cycle notation of the result can be obtained by taking the cycle notation for I florin and applying I euro to all the entries in it. Matrix representation: one can represent a permutation of 1, 2. N is an N matrix. There are two natural ways to do so, but only one for which multiplications of matrices corresponds to multiplication of permutations in the same order. This is the one that associates to I florin the matrix M whose entry me, J is 1 if I equals I florin, J, and 0 otherwise. The resulting matrix has exactly one entry 1 in each column and in each row, and is called a permutation matrix. Here is a list of these matrices for permutations of 4 elements. The Cayley table on the right showed these matrices for permutations of 3 elements. Permutation of components of a sequence: as with any group, one can consider actions of a symmetric group on a set, and there are many ways in which such an action can be defined. For the symmetric group of 1, 2, N there is one particularly natural action, namely the action by permutation on the set Xn of sequences of n symbols taken from some set X. As with the matrix representation, there are two natural ways in which the result of permuting a sequence by I florin can be defined, but only one is compatible with the multiplication of permutations. With the multiplication rule used in this article, this is the one given by. This means that each component I ends up at position I florin, I, in the sequence permuted by I florin. Permutations of totally ordered sets: in some applications, the elements of the set being permuted will be compared with each other. This requires that the set S has a total order so that any two elements can be compared. The set 1, 2, N is totally ordered by the usual permale currency relation, and so it is the most frequently used set in these applications, but in general, any totally ordered set will do. In these applications, the ordered arrangement view of a permutation is needed to talk about the positions in a permutation. Here are a number of properties that are directly related to the total ordering of S: ascents, descents and runs. An ascent of a permutation in I florin of n is any position ELAN where the following value is bigger than the current one. That is, if I florin n equals AI1 florin I2 florins I florin n, then I is an ascent if I florin E AI florin I plus 1. For example, the permutation 3,452,167 has ascents 1, 2, 5, 6. Similarly, A descent is a position ELAN with I florin EA I florin I plus 1, so every I with either is an ascent or is a descent off I florin. The number of permutations of n with k ascents is the Eulerian number. This is also the number of permutations of n with k descents. An ascending run of a permutation is a non-empty increasing contiguous subsequence of the permutation that cannot be extended at either end. It corresponds to a maximal sequence of successive ascents. By contrast, an increasing subsequence of a permutation is not necessarily contiguous, it is an increasing sequence of elements obtained from the permutation by omitting the values at some positions. For example, the permutation 2,453,167 has the ascending runs 245, 3, and 167, while it has an increasing subsequence 2367. If a permutation has Ka1 descents, then it must be the union of k ascending runs. Hence, the number of permutations of n with k ascending runs is the same as the number of permutations with Ka1 descents. Inversions. An inversion of a permutation in I florin is a pair of positions where the entries of a permutation are in the opposite order, and so a descent is just an inversion at two adjacent positions. For example, the permutation I florin A equals A23,154 has three inversions, for the pairs of entries. Sometimes an inversion is defined as the pair of values itself whose order is reversed. This makes no difference for the number of inversions, and this pair is also an inversion in the above sense for the inverse permutation I florin A1. The number of inversions is an important measure for the degree to which the entries of a permutation are out of order. It is the same for I florin and for I florin A1. To bring a permutation with k inversions into order, by successively applying adjacent transpositions, is always possible and requires a sequence of k such operations. Moreover, any reasonable choice for the adjacent transpositions will work. It suffices to choose at each step a transposition of I and I plus 1 where I is a descent of the permutation as modified so far. This is so because applying such a transposition reduces the number of inversions by R1. Also note that as long as this number is not 0, the permutation is not the identity, so it has at least one descent. Bubble sort and insertion sort can be interpreted as particular instances of this procedure to put a sequence into order. Incidentally, this procedure proves that any permutation I florin can be written as a product of adjacent transpositions. For this, one may simply reverse any sequence of such transpositions that transforms I florin into the identity. In fact, by enumerating all sequences of adjacent transpositions that would transform I florin into the identity, one obtains a complete list of all expressions of minimal length writing I florin as a product of adjacent transpositions. The number of permutations of n with k inversions is expressed by a Mahonian number. It is the coefficient of xk in the expansion of the product, which is also known as the q factorial, n, q. A. The expansion of the product appears in necklace. Permutations and computing, numbering permutations. One way to represent permutations of n is by an integer n with 0 aa permil na an. Provided convenient methods are given to convert between the number and a representation of a permutation as an ordered arrangement. This gives the most compact representation of arbitrary permutations, and in computing is particularly attractive when n is small enough that n can be held in a machine word. For 32-bit words this means now a permil 12, and for 64-bit words this means now a permil 20. The conversion can be done via the intermediate form of a sequence of numbers dn, n1, d2, d1, where d is a non-negative integer less than I. The first step then is simply expression of n in the factorial number system, which is just a particular mixed radix representation, where for numbers up to n, the bases for successive digits are n, na1, 2, 1. The second step interprets this sequence as a lemma code or as an inversion table. In the lemma code for a permutation in I florin, the number dn represents the choice made for the first term I1 florin, the number na1 represents the choice made for the second term I2 florins among the remaining na1 elements of the set, and so forth. More precisely, Each dn plus 1 ai gives the number of remaining elements strictly less than the term I florin I. Since those remaining elements are bound to turn up as some later term I florin j, the digit dn plus 1 ai counts the inversions involving I as smaller index. The inversion table for I florin is quite similar, but here dn plus 1 ak counts the number of inversions where chi equals ai florin j occurs as the smaller of the two values appearing in inverted order. Both encodings can be visualized by a NAR-by-RN-ROT diagram in which dots at mark the entries of the permutation, and a cross at marks the inversion. By the definition of inversions, a cross appears in any square that comes both before the dot in its column, and before the dot in its row. The lemma code lists the numbers of crosses in successive rows, while the inversion table lists the numbers of crosses in successive columns. It is just the lemma code for the inverse permutation, and vice versa. To effectively convert a lemma code dn, no1, d2, d1 into a permutation of an ordered set S, one can start with a list of the elements of S in increasing order, and for I increasing from 1 to n set I florin I to the element in the list that is preceded by dn plus 1 ai other ones, and remove that element from the list. To convert an inversion table dn, no1, d2, d1 into the corresponding permutation, one can traverse the numbers from d1 to dn while inserting the elements of S from largest to smallest into an initially empty sequence. At the step using the number d from the inversion table, the element from S inserted into the sequence at the point where it is preceded by d elements already present. Alternatively, one could process the numbers from the inversion table and the elements of S both in the opposite order, starting with a row of n empty slots, and at each step place the element from S into the empty slot that is preceded by d other empty slots. Converting successive natural numbers to the factorial number system produces those sequences in lexicographic order, and further converting them to permutations preserves the lexicographic ordering, provided the lemma code interpretation is used. The sum of the numbers in the factorial number system representation gives the number of inversions of the permutation, and the parity of that sum gives the signature of the permutation. Moreover, the positions of the zeros in the inversion table give the values of left to right maxima of the permutation, while the positions of the zeros in the lemma code are the positions of the right to left minima. This allows computing the distribution of such extrema among all permutations. A permutation with lemma code dn, no1, d2, d1 has an ascent nai if and only if d are permuln d plus 1. Algorithms to generate permutations. In computing, it may be required to generate permutations of a given sequence of values. The methods best adapted to do this depend on whether one wants some randomly chosen permutations, or all permutations, and in the latter case if a specific ordering is required. Another question is whether possible equality among entries in the given sequence is to be taken into account. If so, one should only generate distinct multi-zit permutations of the sequence. An obvious way to generate permutations of n is to generate values for the lemma code, and convert those into the corresponding permutations. However, the latter step, while straightforward, is hard to implement efficiently, because it requires n operations each of selection from a sequence and deletion from it, at an arbitrary position. Of the obvious representations of the sequence as an array or a linked list, both require about n2/4 operations to perform the conversion. With n likely to be rather small, it is not too much of a problem, but it turns out that both for random and for systematic generation there are simple alternatives that do considerably better. For this reason it does not seem useful, although certainly possible, to employ a special data structure that would allow performing the conversion from lemma code to permutation in O, and log n, time. Random generation of permutations. For generating random permutations of a given sequence of n values, it makes no difference whether one means apply a randomly selected permutation of n to the sequence, or choose a random element from the set of distinct permutations of the sequence. This is because, even though in case of repeated values there can be many distinct permutations of n that result in the same permuted sequence, the number of such permutations is the same for each possible result. Unlike for systematic generation, which becomes unfeasible for large n due to the growth of the number n. there is no reason to assume that n will be small for random generation. The basic idea to generate a random permutation is to generate at random one of the n sequences of integers d1, d2, dn satisfying 0 a permil currency din and to convert it to a permutation through a bijective correspondence. For the latter correspondence one could interpret the sequence as a lemma code, and this gives a generation method first published in 1938 by Ronald A. Fisher and Frank Yates. While at the time computer implementation was not an issue, this method suffers from the difficulty sketched above to convert from lemma code to permutation efficiently. This can be remedied by using a different bijective correspondence, after using D to select an element among I remaining elements of the sequence, rather than removing the element and compacting the sequence by shifting down further elements one place, one swaps the element with the final remaining element. Thus the elements remaining for selection form a consecutive range at each point in time, even though they may not occur in the same order as they did in the original sequence. The mapping from sequence of integers to permutations is somewhat complicated, but it can be seen to produce each permutation in exactly one way, by an immediate induction. When the selected element happens to be the final remaining element, the swap operation can be omitted. This does not occur sufficiently often to warrant testing for the condition, but the final element must be included among the candidates of the selection, to guarantee that all permutations can be generated. The resulting algorithm for generating a random permutation of A0, A1, NA1, can be described as follows in pseudocode. For I from n down to 2, do a D a random element of 0. IA1, swap a, D and A, IA1. This can be combined with the initialization of the array A, I, equals I as follows. For I from 0 to now 1, do a D plus 1 a random element of 0. I, AA, D plus 1, a, D plus 1, AI. If D plus 1 equals I, the first assignment will copy an uninitialized value, but the second will overwrite it with the correct value I. Generation in lexicographic order. There are many ways to systematically generate all permutations of a given sequence. One classical algorithm, which is both simple and flexible, is based on finding the next permutation in lexicographic ordering, if it exists. It can handle repeated values, for which case it generates the distinct multi-zit permutations each once. Even for ordinary permutations it is significantly more efficient than generating values for the lemma code in lexicographic order and converting those to permutations. To use it, one starts by sorting the sequence in increasing order, and then repeats advancing to the next permutation as long as one is found. The method goes back to Narayana Pandita in 14th century India, and has been frequently rediscovered ever since. The following algorithm generates the next permutation lexicographically after a given permutation. It changes the given permutation in place. Find the largest index k such that A, k plus 1. If no such index exists, the permutation is the last permutation. Find the largest index L greater than k such that A, k, L. Swap the value of A, k, with that of A, L. Reverse the sequence from A, k plus 1, up to and including the final element A, n. For example, given the sequence 1, 2, 3, 4, which starts in a weakly increasing order, and given that the index is zero-based, the steps are as follows: index k equals 2, because 3 is placed at an index that satisfies condition of being the largest index that is still less than A, k plus 1, which is 4. Index L equals 3, because 4 is the only value in the sequence that is greater than 3 in order to satisfy the condition A, k, L. The values of A, 2, and A, 3, are swapped to form the new sequence, 1, 2, 4, 3. The sequence after k index A, 2, to the final element is reversed. Because only one value lies after this index, the sequence remains unchanged in this instance. Thus the lexicographic successor of the initial state is permuted, 1, 2, 4, 3. Following this algorithm, the next lexicographic permutation will be 1, 3, 2, 4, and the 24th permutation will be 4, 3, 2, 1, at which point k plus 1, does not exist, indicating that this is the last permutation. Generation with minimal changes. An alternative to the above algorithm, the Steinhauser-Johnson-Trotter algorithm, generates an ordering on all the permutations of a given sequence with the property that any two consecutive permutations in its output differ by swapping two adjacent values. This ordering on the permutations was known to 17th-century English bell ringers, among whom it was known as plane changes. One advantage of this method is that the small amount of change from one permutation to the next allows the method to be implemented in constant time per permutation. The same can also easily generate the subset of even permutations, again in constant time per permutation, by skipping every other output permutation. An old paper proposed a very efficient algorithm called Heap's permutation generation algorithm. An article authored by Robert Sedgwick said that this algorithm is the fastest algorithm of generating permutations in applications. Mendrick permutations. Mendrick systems give rise to Mendrick permutations, a special subset of alternate permutations. An alternate permutation of the set 1, 2. 2n is a cyclic permutation such that the digits in the cyclic notation form alternate between odd and even integers. Mendrick permutations are useful in the analysis of a RNA secondary structure. Not all alternate permutations are Mendrick. A modification of Heap's algorithm has been used to generate all alternate permutations of order n without generating all permutations. Generation of these alternate permutations is needed before they are analyzed to determine if they are Mendrick or not. The algorithm is recursive. The following table exhibits a step in the procedure. In the previous step, all alternate permutations of length 5 have been generated. 3 copies of each of these have a 6 added to the right end, and then a different transposition involving this last entry and a previous entry in an even position is applied. Software implementations, calculator functions. Many scientific calculators and computing software have a built-in function for calculating the number of k permutations of n. Casio and TI calculators, NPR, HP calculators, Perm, Mathematica, falling factorial, spreadsheet functions. Most spreadsheet software also provides a built-in function for calculating the number of k permutations of n, called permut in many popular spreadsheets. Applications. Permutations are used in the interleaver component of the error detection and correction algorithms, such as turbo codes. For example, 3GPP long-term evolution mobile telecommunication standard uses these ideas. Such applications raise the question of fast generation of permutations satisfying certain desirable properties. One of the methods is based on the permutation polynomials. Also as a base for optimal hashing and unique permutation hashing. See also. Notes. References: Bogart, Kenneth P., Introductory Combinatorics, Harcourt Brace Jovanovic, ISBN A0-15-541576 Zab, Bar Cube Na, Mikla Cubed S, Combinatorics of Permutations, Chapman Hall CRC, ISBN A1-58488-434-7 Bruldi, Richard A., Introductory Combinatorics, Prentice Hall, ISBN A978-0-13-600 2040-0 Cameron, Peter J., Combinatorics, Topics, Techniques, Algorithms, Cambridge University Press, ISBN A0-521-45761-0 Carmichael, Robert D. 1937, Introduction to the Theory of Groups of Finite Order, Dover, ISBN A0-486-60300-8 Eckstein, Larry J., Discrete Mathematics and Algebraic Structures, W. H. Freeman and Company, ISBN A0-7167-1804-9 Donald Knuth. The Art of Computer Programming, Volumia 4, Generating all tuples and permutations, Fasciclia 2, first printing. Edison Wesley, 2005. ISBN 0-201-85393-0. Donald Knuth. The Art of Computer Programming, Volumia 3, Sorting and Searching, 2nd edition. Edison Wesley, 1998. ISBN 0-201-89685-0. Section 5.1 Combinatorial Properties of Permutations, pp 11 72. Hall, J.R., Marshall, The Theory of Groups, Macmillan, Humphreys, J.F., A Course in Group Theory, Oxford University Press, ISBN A978-0-19-853459-4. Rotman, Joseph J., Advanced Modern Algebra, Prentice Hall, ISBN A0-13-087868-5. External links, Haswinkel, Michiel, ed., Permutation, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4a.